I just love this picture of Einstein. Evidently, he was quite the celebrity, and at some point got tired of having his photograph taken. But anyway, let's go on to general relativity, and we're going to be very general here. I actually ran into somebody who got a PhD in theoretical physics and asked this person some questions about general relativity, and he said, "Well, you know, not that many people actually understand all of general relativity. It's a fairly difficult topic, but the principles we can understand." So if you recall, in special relativity, we said there was no experiment you could do to determine whether you're moving and somebody's sitting still, or somebody's sitting still and you're moving, right? Wait, those are the same thing. But whether they're moving or you're moving, right? Okay. So the principle of equivalence for general relativity is this, okay? There's no experiment that will discern the difference between the effect of gravity and the effect of acceleration, okay? Another way to say it also is that gravitational and inertial mass are equivalent, right? And this is sort of an interesting thing. Let's look at the second thing, and then we'll look at the first thing, okay? The second thing is just this, right? Is that that I can exert a force on something, right? And F equals ma. This is our inertial mass, right? That's our inertial mass. And then when we've got G is equal to F over m, that's gravitational mass. Now notice that this equals then F equals mg, right? Okay, this is gravitational mass. And we have always assumed that they are the same, right? Because imagine if they were different, right? How hard it would be. But this is the principle of equivalence, right? Is that the gravitational and inertial mass are equivalent, okay? So if you look at this, if you have a mass and you're exerting a force on it, it could be that you're resisting a gravitational field, or it could be that you're simply trying to speed up the mass. Let's think about this in another way. Okay, here's a couple pictures, right? Let's imagine that you're in this box in this room, and on Earth, if we drop a book, right? And if this is an elevator, let's assume that it's moving at a constant speed, that it's not accelerating, or it's not moving. Let's say it's not moving, right? If we drop a book, the book accelerates to the floor. And we say it does that because there's a gravitational field that accelerates it to the floor, right? If we were in space accelerating this way, right, and this is, of course, the direction you have to accelerate to mimic this situation, right? We would drop the book, and the frame of reference would continue to accelerate up. The book would stop accelerating, and we would see the same thing, that the book would accelerate toward the floor at 9.8 meters per second, right? And so what we're saying is that there's no difference between being at rest on Earth and being in a spaceship far away from a gravitational field and accelerating that way. There's no experiment that this person could do to discern the difference between a uniform gravitational field and being in a box that's being accelerated that way. They are absolutely equivalent. We could sit there and figure out what this force is. This force would be mg. This force would be ma. Right? And these masses are equivalent. Anyway, there you go.